Hello, my name is Mike Galley with ECS Mid-Atlantic, here to present full depth reclamation mix design for VDOT. Now, before we get into the presentation, just a quick little background on myself. I'm a principal engineer, South Regional Manager for ECS, and have been in the geotechnical construction materials testing consulting industry for about the last 35 years. And during much of that time, I've been involved with soil stabilization, pavement reclamation practices, including at the onset of when VDOT first started the full depth reclamation process. During that time, I have been involved on numerous projects across the state, working with multiple districts, which also included reviewing VDOT special provision sections through the multiple iterations. So with that, I'd like to start with our presentation. And before we get to this particular part of the process in the full depth reclamation, it's important to note that in the VDOT procurement process, the actual pavement design or the pavement design section has already been completed by this stage of the contract. So once the pavement and the thicknesses have already been determined, the procurement process will fall on the contractor typically as the next stage of the implementation of the mix design and have that responsibility for the verification process. So to go over the FDR process, just a couple objectives. You know, the whole process is we're trying to mimic as best as we can in the lab the conditions and the environment of what's going on in the field. So we'll give a kind of a brief definition, go over the standards, talk about the stabilization methods, there's 3 of them, the applications, and then we'll get into the actual job mix formula as it's identified in VDOT special provision. And then we'll go into the mix design submittal and some challenges, some lessons learned over the years that I've experienced. Basically, full depth reclamation is a pavement recycling technique in which the existing asphalt pavement and a predetermined portion of the underlying materials are pulverized, blended, and stabilized in place. Typically, this is going to include the pavement material, the subbase aggregate, and the subgrade soils, or some iteration of all 3 of those. And basically, it's just a milling drum with a cutting blade. And as the drum is advanced, it is cutting up and blending and mixing the distressed asphalt layer, whatever portion of granular base, and whatever portion of the subgrade soil. And again, this is the process that occurs in the field of which we're trying to mimic and replicate in the laboratory. Now the standards, VDOT has a special provision section that was created, one, through their experience base that they've currently developed over the years, but generally in accordance with the ERA Basic Asphalt Recycling Manual, which is also in accordance with the Federal Highway Administration. But basically, the special provision section, it covers every aspect of what is required of a contractor or a mixed design process, which is the materials, the QC plan, the job mix formula, which is specific for our discussion today, the types of equipment, the trial section, acceptance testing, measurement and payment. It's basically everything that is going to be required contractually in the submission process for full depth reclamation design. Now there are 3 basic stabilization methods: mechanical, bituminous, and chemical. Chemical is going to be a predominant discussion today because that's the most readily applied across all of the VDOT roadways. But basically, mechanical stabilization, you're just adding in granular materials, whether it's new aggregate, wrap, crushed concrete, you're adding in material and you're using that as your basis of improvement of your pavement section, or sub-base section, I should say. Bituminous stabilization, you're adding in emulsified asphalt or foam asphalt and making that be part of your stabilized base. Again, for our primary discussion is chemical stabilization. Portland cement is the most common chemical stabilization that's added in the FDR process. Sometimes you might add lime and sometimes fly ash, or some kind of blend of all of these particular type of materials. But again, Portland cement is the most common, and we'll look at why that typically is the most common chemical use. Now, some of you may be familiar with this type of chart, but it's basically a soil classification chart based off of gradation in accordance with the USCS and also AASHTO classification system. And as you can see, these really three, they list four, but it's really three versions of stabilization process: the emulsified asphalt, foamed asphalt, and cement. You can see the range of the type of materials or the type of soils that these particular processes may be the best suited for. And you can see lime down at the very bottom. It's got the least amount of range, but it does cover a couple soil types. Now, as you see, cement has covers most of the soil classifications in the system. Although I would argue outside of an organic layer, which you really shouldn't be using organic layers in anything, the elastic silt and the fat clay, I have seen and we have used cement as part of the reclamation process, and that has worked very well. As long as your predominant source is your asphalt and your aggregate base, and pulling up and having some elastic silt and fat clay as a small portion of that matrix, cement still works very well. Now on to the actual mix design, the job mix formula. Now, the hardest part of this entire process, or the goal of this process, is we're trying to mimic as best as we can in the laboratory the field process. We don't have all the readily available tools that they do in the field to collect our samples. So there's different manipulation techniques that we've done and developed over the years that can help get as close to the field conditions as we can in the laboratory. But basically, the laboratory mix design is conducted to determine and optimize the percent of stabilizing agent, again, typically cement, and the physical properties of the mixture. It's primarily based off of strength, and of course, a big component of that is the moisture content. Now, again, the primary chemical stabilization agent is cement throughout most of these applications that you'll see. And here is just a chart that you see that covers a couple different ranges of cement and a different range of compressive strength in PSI. Now, one of the most critical things in understanding in sampling process is a project meeting. It's having an understand of any historical data of the roadway. Before you get out to the road, you need to know what is the roadway made of, and understanding the planned roadway design, including the shoulders. And I'll discuss why the shoulders are equally important. But you need to know the design depth, the thickness, and elevations. As I said at the very first slide or the onset of this presentation, VDOT has already determined, whether it's VDOT or VDOT's design engineer of record, has already determined the new pavement design, which includes the FDR thickness that makes up their design. So we need to understand exactly, because of elevation, the thickness of our sample depth. And then we need to also understand the construction sequence. What is the contractor planning to do, or how are they planning to blend this material in place? Do we need to mill a little bit before we collect our sample? How they're going to move the soils around, or the blend of matrix around, such that we can make sure that what we're sampling is exactly what they're going to do in the field. Now, when we do collect a sample, we're collecting blended samples of the pavement structure, and again, at the correct elevation and location. This is very critical in the field sampling part of this process. Now, once again, it's very important to know and understand if there's any pre-cut or fill. And this has to do with the elevation of the existing roadway and what the planned elevation of the final surface pavement is going to be. And how are the shoulders going to be handled? Are they going to be implemented in part of the FDR process? And were the shoulders similarly in the existing condition as a roadway, or is it going to be a new application? But basically, in accordance with the VDOT special provision, one sample is collected every 2,500 linear feet each lane. Now, as you can imagine, for a long section of roadway, whether it's a 2-lane divided, 2-lane undivided, a 4-lane, or a 6-lane, every 2,500 linear feet per lane, that is a lot of samples. And we'll discuss a little bit later why it's critical to have this understanding and knowledge about what's going to do, because time comes into this factor. But basically, we're obtaining by coring or block cutting or a specialized sampling bit to collect our sample. And we're collecting only the specified depth of materials, and we're turning it to the lab for the processing. Of course, you're going to be digging a big hole in the middle of a VDOT roadway, so patching is a critical element. Typically, cold patch will work. But again, in that meeting that was discussed in the prior slide, you need to make sure it's, the patching technique and method is approved by the design team and VDOT before you even start cutting holes in the roadway. So as you can see in this particular slide, the old method used to be we would saw cut a big block of asphalt out, pull the equivalent amount of aggregate base and or soil out for the correct FDR depth. Then we'd have to bring that big giant asphalt block back to the lab, cut it into smaller sections or pieces, stick it in the oven, soften it up, take a hammer, bust it up, and then continue on with that process until we get a sample that has been broken down adequately for being able to process the samples. This method just did not work very well, and it is not the relevant prevalent method that we would like to use. So next, another sampling technique. This is a small little unit that a contractor has, and it's basically used for curb cuts and things like that around edges. But it's basically a mini little milling machine. And as you can see, it cuts a very small section. It grinds up the asphalt. It kind of blends the material, and you can set it to the correct depth of what you need to sample to. And you can see from as the small little milling head has been risen or raised, you can see that it's really ground up the material. And this is one of the optimal units that can be used to collect samples, because that is one of the devices that they're using, and that processes the material as close as it can to actual field conditions. Another method that we've used, and this has been the most successful and most readily available, this is a sample bet that was kind of mimicked to what North Carolina DOT, but it's basically just a grinder head with teeth that mounts on the back of a standard SPT drill rig. And you can see as they are grinding the asphalt section, it cuts up the asphalt, it breaks it down very uniformly, and as they extend to the correct sample depth, it is then blending and mixing all of the materials together to the correct depths. And here's just a couple little photos of the blending process. So basically, once you get through the asphalt, you go to the correct depth that's easily measured, and you just let the head just rotate and turn for a couple seconds as it blends the material for you. Then you just collect the samples, bring them back in buckets, patch the hole, and you're done. Now, that doesn't mean that you can then immediately go right to lab testing. There's some processing that still needs to potentially occur to make sure the asphalt is broken down, or you don't have large chunks that aren't broken down properly. So some processing needs to occur, but this is what we have found to most closely represent actual field conditions. And the results have been pretty reliable and very accurate for active projects. Now, it's important for all laboratory testing, as with the field, but laboratory testing is to follow the testing standards. This is a text or table that is pulled right out of the VDOT Special Provision section that covers the variety of tests in the test method standards that's required depending on what you're actually doing. Such as, one of the biggest mistakes I've seen in the FDR process is the moisture density relation. A lot of firms will refer it back to the ASTM D698, basically the standard Proctor, and or the VTM1, where you're separating out what's passing the number 4 and then doing an oversized correction factor for the Proctor curve. That's not the method we do in FDR. It follows AASHTO T134. So if you do not have the specification, you cannot do this test, and you must get the specification so you understand how to do this test properly. And you can see here the other predominant specification used is compressive strength of soil cement cylinders. That's a spec that we utilize for FDR, or VDOT uses for FDR, and that is the ASTM D1633. And basically the criteria is we're looking for a minimum and maximum compressive strength at 7 days. The minimum is 250, the maximum is 450. And we'll talk about why are those critical threshold numbers, and why does VDOT look at those as being the critical threshold value. And there's some other sections here, again, depending on if you're doing foamed asphalt or the emulsion asphalt. So basically, again, we're processing samples collected from the field to mimic actual field gradations. And again, this is where the largest errors occur. We do the gradation in accordance with VTM 25. The design range is not that hard to hit, really, and can be hit in most applications, is 100% passing the number 2-inch sieve and 55% all particles passing the 3/8-inch sieve. And what this allows us to do at this stage before anything's done is we're determine the suitability of stabilized materials, whether or not it's too coarse or too fine. This is a stage that we can implement and let the design team know whether or not we've met a gradation criteria for that particular project. The next, again, is we step into the moisture density relations, which is, again, AASHTO T134, and then we mold our compressive strength cylinders, and then we'll do compressive strength testing on the pills, again, between 250 to 450 psi. If a strength is below 250, it's been determined that we don't believe that the section is strong enough to support the design criteria for what the roadway design has been established to. If you start getting strength above 450, the concern is you might have too much cement blended into the material and may become too rigid. And then there's a fear of shrinkage cracks that can propagate up through the asphalt section. So we really like to have the sweet spot between 250 to 450 psi. Again, the critical note on AASHTO T134, you're using all the material passing the number 3/4 sieve. That's one of the biggest changes of this particular process that's different than the other typical standard Proctor methods. And there is no oversized correction. The process, T134, it does have a certain gradation criteria on how you process the materials. So you need to read that very carefully to understand how you're implementing that. But basically, it isn't much different than 3 equal layers, 25 blows per layer with the standard Proctor. And you're going to vary the moisture content plus or minus 2%. That's typical in any particular moisture density relation curve. You're going to add cement to the material. And it is important, there is a time of preparation. Anywhere from half hour to 2 hours, you want to make sure everything's blended. You want to make sure that the Proctor is done before the cement has any time to hydrate and set up. But you do want to make sure that the cement has absorbed and blended in from the moisture content and also the soil conditioning. Again, you want to use fresh cement. And the typical increments for cement is you're going to run basically 3 batches at 3, 4, or 5% cement, or 3, 5, and 7% cement. I would recommend, if you're not familiar with the soil types or this process, you develop a wider range so you can draw some linear curves of the 3, 5, and 7%. However, most applications that we've been involved in, the sweet spot is right around 4% plus or minus, depending on the fine or the coarseness of the materials. Once you get your Proctor and establish your optimum density and also then your optimum moisture content, you're going to make your molded soil cement cylinders in accordance with ASTM D1633. Typically, you're going to be using method A, as most blends of the aggregate is, which is a 4-inch split Proctor mold. And again, you're utilizing everything that's passing the 3/4 inch sieve. You're going to compact at the optimum moisture content and as close to optimum density as you can. Now, important to note, in between each layer, as you're molding the specimen, no different than with the proctor, you're going to scarify the top of your first layer and the second layer. And what this does is it effectively reduces the chance of a shear plane when you actually put it in a unconfined compressive strength machine. Once you get your samples processed, as you can see in the top picture representation, those are your soil cement pills. You're going to cure them in a moist room, protected from free water for 7 days. And then you're going to pull them at 7 days, and you're going to immerse them in water for 4 hours prior to testing. Now, this is in accordance with ASTM 1633. So similar to T134, you need to make sure to have the correct ASTM standard and make sure you follow it to reduce any chance of errors. And you're going to cap the samples in accordance with ASTM D1632, which is typically a sulfur capping compound. Now, once you have the compressive strength specimens molded, you've done the curing process, they're ready to be broken, you need to make sure you have the proper equipment. You cannot break these specimens on a typical concrete break machine. The typical concrete break machine is calibrated, or it has a 500,000 pound load cell, and it's just not calibrated in the low range of what these strength specimens may be broken at. This is a picture of a typical, most of your geotechnical soil labs have this. It's a CBR machine and or a unconfined compressive machine. These typically are a 10,000 pound load cell, and those are calibrated at these much lower strength ranges of which we're breaking these specimens at. Now, as you see on this also, we have the proper head, the proper sized head that's specific for the soil cement cylinders, or the FDR cylinders. You should not, once again, be breaking this with the 6-inch compression head that you might have on a concrete break machine. So once again, it's critical to have the proper equipment in order to conduct this test. Now, once you've done that, this is just a simple linear graph that we've plotted the results of. You can see for each particular sample, FDR number 1, 2, 3, 4, and such, at the different cement ranges. In this one here, we did 3, 4, and 5, and we've outlined or highlighted the unconfined compressive strength range 250 to 450. And basically, you're just trying to find the optimum cement content that meets this criteria. You don't need to use 5% cement if you can get it done at 4%. That's a cost savings for the client, and it meets VDOT's requirements. Now, the mixed design submittal, this is where it's very critical. As you can see, the mixed design submittal is supposed to be submitted to VDOT or the engineers for 30 working days prior to the planned start of the project. And at a minimum, the mixed design submittal should include the target field density, basically your proctors, the percentage weight of all the stabilizing agents, so they can see and know what is the range of cement that's going to give you the optimal strength requirement. What is the moisture content that's going to be required, because this becomes critical in the field as part of the QC monitoring process. Now, if you're using foamed asphalt or emulsion, again, there's additional specifications required to submit on that. That's part of the ASTM process. And then the target gradation. You know, you determine at the very first test whether or not any additional materials need to be added. So if something needs to be added outside of the chemical, then you need to include that as part of the process. But these are the predominant requirements as part of the submittal process. Now, as I indicated, 30 working days prior to the planned start of the work. Depending on your length of roadway and how many lanes you have, this may be a hard target to hit, or you need to make sure everybody understands how much time is needed to perform the laboratory testing. Because you can imagine, for a long roadway, multiple lanes, getting one sample every 2,500 linear feet, you're running 3 proctors at every point. Again, each proctor will have its own cement point, which requires 3 at each particular location. That's a lot of sampling to process, and you got to make sure you have the time to conduct the test. Then after you do that, you got to let it soak for 7 days before you can even break it. So the challenges is understanding the test standards, making sure you have the correct testing methods and following those testing methods. The next thing that's a challenge is understanding the elevation of the roadway. Understanding that you might not be collecting your 12-inch FDR section starting at the surface of the existing roadway. It may require 2 or 4 inches of the roadway to be milled to then start collecting your 12-inch sample. And then also understanding and knowing what is the design section. What did the design engineer of record set as the FDR depth that's part of his pavement design? Now, I mentioned the shoulders before. Shoulders have provided some issues in the past. If the shoulders are not in the current condition of the existing roadway, and they're looking at expanding or extending into a wider shoulder, you need to understand, are those materials going to be the same as the existing roadway, or do they need to build up that shoulder in some methodology? So the shoulders maybe have to treat it totally differently than the actual roadway section. So it's understanding what's happening on the shoulder. Again, whether or not the matrix of the sample material is too gravelly or too sandy. And there are different techniques that you can utilize to add aggregate back in, again, getting into multiple techniques at one time, or if it's too sandy where you need to add some fines to the material. I've seen issues before where old cement, sometimes you go ahead and collect cement for one particular project, and then you don't do another one for 6, 8, 10 months, and you might try to use the same batch of cement. I typically always recommend whatever contractor or whatever cement source that the contractor is going to be using, you get a sample of that actual material that they're going to be utilizing in their matrix to make sure that whether it's type 1, type 2 material, that's exact what you're doing in the lab. And again, time critical sampling and testing. There's a lot of samples. There's been many projects, even a small project, where we're doing 96 proctors. And then of those 96 proctors, every sample has to have 2 compressive strength specimens made. And then you sit on it for 7 days before you do it. So there's a lot of time involved. You need to make sure you have the time to process in application. So I believe we've covered all of the relevant information on full depth reclamation mix design. Hopefully you've learned a little bit from this presentation and what it takes to do the proper field sampling and also laboratory testing for a standard FDR mix design process. I'm happy to speak with anyone if anyone has any questions after this presentation. Feel free to reach out because I believe it is important in the industry that we are doing all this correctly for VDOT. And with that, I thank you for your time.